My name is Junior Costa de Jesus, and I will be presenting the paper Depth-CUPRL in IROS 2022. So my motivation for this paper is to present a technique that learns depth maps and extract meaningful information for the control of aerial vehicles and bring a high performance for Deep-CUPRL networks, as Deep-CUPRL networks are not sample efficient in the case of using high-dimensional observation, as in the work of Ricardo Granda, that he uses only the laser inputs as the states for the control through Deep-CUPRL techniques. And my goal is to make the navigation from a UAV, and to do this, what I did is to make the depth estimation through the inputs of the camera, and I trained a network that learned these estimations, and the depth network are trained in the KITS dataset, and after that we fine-tune them to work in the simulated environments. And with the depth maps, we can extract the representations through constructive learning, and these representations are passed to the reinforcement learning algorithms that make the optimal decisions for navigating in the aerial vehicles. And in my method, we will receive the visual input from this vehicle, transform them in depth maps, and this experience from the robots will save in a prioritized memory. And this memory, we can extract these observations, and what I do from the depth observation, we split them in two and make a data augmentation from them. And with this, we try to learn through constructive learning the representations from these inputs. And through these representations, we can make the best action for the robot through visual inputs. So I gave a reward from colliding and navigating, and as he collides, he receives a negative reward, and when navigating, he receives a positive reward. Very simple. And what he wants to optimize is to make the robot navigating without colliding with any object. So in my experimental setup, I did the two environments, and one more simple and one more complex. And in my network architecture, I split them in the actor network and critic network. And these networks that are compared with my method, the architecture from them are close to what I used in my work, trying to make it more close and to see what is the best results of these techniques that we experimented. In the results from the first environment, we can see that only the Curl Classic didn't converge for the best reward, the best reward in the train. So we can see that only the pixel inputs, they weren't capable of having a success rate on the evaluation part. The evaluation is when the robot is not training, is after the end of training, and you can see that the depth inputs have a best success rate in this first environment. In the second environment, we can see that the results are more unstable, and the closest to the optimal reward evaluation, the training, is our method, the Depth-CUPRL. The others get close, but not much. And the Curl Classic didn't converge for this optimal reward that we want for the training. In the evaluation part, we can see that the depth the depth inputs have the best success rate, and so we saw the impact from converting these pixel inputs to depth and using them in a curve architecture. After that, we see without these image representations to see how much success would they have with the SEC network. And using the prioritized memory, you can see that we have the best success rate in our work. In my method, I use the curve network and the prioritize representations from these memories. And my contributions, I present a novel Deep-CUPRL method based on extracting information from depth estimations, and we could have a best performance in obstacle avoidance in UAVs, and the Depth-CUPRL presents a best performance in the state of art in terms of image-based IRL approach. So introducing the representations from these images and the use of prioritized memories, we generated the best navigation in our tests. And these are the institutions that collaborate for this research. Thank you.